Hello, and I welcome you to the revision of the Industrial Electronics N3 paper that was written in August 2024. So, without wasting much of the time, let me quickly go into the revision of the paper. And for the sake of time and progress, I will ignore the instructions for now, but I do advise us that when we are in the exam, kindly go through the instructions to understand them. It's very, very important, most particularly where it says, like for example, the or final answers must be approximated accurately to 3 decimal places. It's very important, as a matter of fact, to go through all instructions to understand them. It's very, very important. So I'm starting at section A, question 1. 1.1 is saying various options are given as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question and number. 1.11 to 1.1.5 in the answer box. So 1.1.1 is saying Peter is using a multimeter but reads the measurements incorrectly. This type of error is an or a dash error. That's a gross error because it's also called a human error. So our answer is C. Just out of interest, I just want to highlight again the other ones. Right, we have 3 types of errors as a matter of fact. We have gross errors that are as a result of a direct result of mistakes made by humans. And of course, we have systematic errors, which are classified into 2. They have 2 categories. They have instrumental errors and they have environmental errors. So instrumental and environmental, they fall under systematic errors. Then lastly, we have random errors. And these are just caused by unknown factors. So we call them random errors, right? These are the errors that we have just out of interest. I went through that. So 1.1.2, a dash method is used to switch an SCR off in a DC circuit. That's a forced commutation. That's B actually. Just it might interest us also to just know that commutation is a method of actually turning off the SCR from an on state to off. Right, and so it's just good to know that as well. Okay, right. By the way, the other 3, phase control, cyclonic control, cycle control, they are methods of control where the SCR is used as a control. Since it's a high-speed rapid action switch, it is widely used in areas of electronic control, speed control, temperature control, etc., etc. Right, so 1.1.3. The output from a dash shunt clipper consists of negative half of the input signal. So that's positive series and positive shunt clipper. That's A there. That's our answer. Right. And in 1.4, the deviation from the true value of quantity being measured is known as the error of instrument, right? So that's actually the description of an error there. 1.1.4 is going to be A, right? 1.1.5, push-pull amplifiers makes use of class, right? It makes use of class AB amplifier. So our answer is C, right? Just out of interest again, in actual fact, many amplifiers are designed for class AB conditions, where a compromise is reached between high efficiency of class B and low efficiency of class A. It's good to know that. So the class AB is there to try and compensate for the shortcomings of class A and the shortcomings of class B. So it meets them halfway, right? So let's quickly go to the next question. That's in 1.2.1. Indicate whether the following statements are true or false by writing only true or false next to the question number in the answer box. Kirchhoff's law, current law, states that the algebraic sum of currents entering a node or junction or a node and the algebraic sum of current leaving the node are equal to 0. That's true, actually. That's true then. Right. Let's go to the next question. The next question is saying, capacitive transducers operate only with a DC current. That's false, apparently. It's not correct. So we say this is true and this is false actually. And in 1.2.3, and an opto-isolator cannot offer isolation between high voltage and low voltage. Actually, that's false as well. An opto-isolator is also the optocoupler. It is the photocoupler or the optocoupler. It is used as an interface actually between the high voltage and low voltage system, because it provides a convenient method of electrically isolating one part of the electrical system from another. That's why actually it is used for that. So it's not correct to say this is false. Right, 1.2.3, 1.2.4 is saying the collector current of an NPN transistor will increase if the base emitter forward bias voltage is increased. That's 1.2.4. That's actually true, right? And then RC coupling amplifiers do not have a good frequency response. That's false, actually. Right, let's go to the next. Choose one term of the following from the list below that matches each of the following descriptions. Write only the answer next to the question number in the answer book. Right, a process that can generate free electrons in the conduction band. That's doping. That's doping them. So we just write here. Right, and 1.3.2, a two-terminal device offering a low resistance when forward biased and high resistance when reverse biased. That's a diode. That's actually a diode. Right, a field effect transistor of which the gate terminal is insulated from the channel. That's a MOSFET, metal oxide semiconductor field effect transistor. That's a MOSFET there. And then dash commutation is applied in SCR when an AC supply is used. That's a line commutation. So we use line commutation, right? And the negative feedback is a process used to improve the performance of a circuit by reducing its gain. So it's by reducing the gain, right? Let's quickly go to the next question. Right, choose a term from column B that matches a description in column A. Write only A to J next to the question number, right, in the answer book. The resistance of an NTC thermistor is proportional to the temperature. That's a negative temperature coefficient thermistor is dash proportional to the temperature. That's inverse. So it's inversely proportional. Inversely, so that's I. That's inversely proportional. An oscilloscope can be used to measure the value of that's from the given. So it's used to measure the value of the voltage. So that's J, the voltage. So that's J there, right? And then in a closed loop system, the output is monitored. And it's true, in a closed system, the output is actually monitored through the feedback, right? So 1.4.4, it's now saying in an N-type material, the Fermi level is closer to the conduction band, that's E, right? And then transition capacitance is due to the charge which exists in the depletion layer under a reverse bias condition. So that's F, right? Under a reverse bias condition, right? So these are the multiple choice questions that we're having. Let's quickly go to the question number 2. And question number 2 is saying, refer to figure 1, determine the following by using Kirchhoff's laws, right? So the question is saying, determine the equation for loop BAFEB. So apparently BAFEB is this loop. BAFEB is this loop, right? According to Kirchhoff's second law, apparently, which is the one we can use here, the EMF in every closed loop is equivalent to the algebraic sum of all the potential differences in that particular loop. So considering loop BAFEB, it means that the EMF we have is only at the source, that's 12 volts. So we can safely say 12. So I'll just indicate it here quickly. 12 is equal to, so that's 12, right? Loop B, A, F, E, B, right? So it's 12 is equal to the potential difference that we have, right? There is a potential difference here. So at every resistance, we happen to have a potential difference. What current is flowing through this branch is I1. So I1 times 6, that's 6I1, right, is equal, so plus, what are the current we see? We see 7 times I1, which is 7I1, right, plus, which are the current again do we notice? 6I1, so plus 6I1 as well. So that marks 6I1, right, and plus, right, we have the 8 ohm resistor here. Now, at the 8 ohm resistor, which current specifically is passing through that, right? Current I1 plus I2 left the battery, and it's subdivided here. We see I2 this side, we see I1 going towards this direction, which means when it recombines at this other junction here, going back to the battery, which means the current we shall see coming back to the battery is the I1 plus the I2. So it means the current that will flow through this is I1 plus what? Plus I2. So it means, therefore, that 12 is equal to 6I1 plus 7I1 plus 6I1 plus 8. So we are including also the 8I1 plus I2. So simplifying that, it means we end up having 6 plus 7 plus 6 plus 7 again, the other one. It means it's going to give us all in total, that's in an 8, so we can, that's giving us 19I1 plus 8I1 plus 8I2, right? Simplifying this bracket here, right? 8 times I1, that's 8I1, 8 times I2, that's 8I2, right? So it means, therefore, 12 is equal to, right, adding again 19 plus 8, that's 27, right, I1 plus 8I2. So definitely we end up having 27 I1 plus 8I2 is equal to 12. That marks the equation. So this is the equation that the examiner was asking for, right? And then the equation for loop BCDEB. So now we are looking at the other loop, right? I'll just quickly clear off, right? And then we are saying, considering loop BCDEB, right? That's our loop that the examiner is asking. Again, we are taking this direction. So we are saying BCDEB. 12 again in that loop, the EMF we have is 12, is equal to the algebraic sum of all the potential differences. It means we have the 12 I2, the potential difference across this resistor here is 12 I2. This one is 5, so plus 5 I2 again, plus 5 I2 again, right? Plus 8 I1 plus I2. So we have already explained why that is 8 I1 plus I2 really. So 12 is equals to, so we can therefore add 12 plus 5, of course, plus 5 again, and of course, plus 8 I1. So we have 12 I2 plus 5 I2 plus 5 I2 plus 8 I1 plus 8 I2. Right, just a simplification that I've done of that bracket. So it means we end up having, it means we have 8 13. That's another 1.3 is now say, determine the magnitude. Take our two equations that we have formed and we now solve them, the two of them, right? So let's solve the two equations simultaneously, right? Where is that taking us to, right? First equation, upon arrangement, it's going to be, right, 27 I1, right, plus 8 I2 is equal to 12. That's our first equation there. The second equation, 8 I1, just an arrangement that I'm making, it saying 30 I2. So I'll start with 8 I1 plus 30 I2 is equal to 12. Doesn't matter actually. Even if I say 30 I2 plus 8 I1 is equal to 12, the way I got it is still fine. That marks my equation 1 and my equation 2. So what am I going to do? I will now formulate equation number 3 using them is the method that I have opted to use. So I will use the first equation to create equation number 3. So making I1 the subject, it means we can therefore directly, making I2 the subject actually, 8 I2 is equal to 12 minus 27 I1, right? And what do we end up having? Okay, divide that by 8. Divide that by 8. It means I now have I2 is equal to 12 minus 27 I1 over 8. So it's still fine. I have made I2 the subject. Right, so I now take it and substitute into the second equation. Right, substituting into the second equation means we now have 8 I1 plus 30 I2 that we're having there is equal to 12. Right, this can be written as, we can actually write it as I2 is equal to 12 over 8 minus 27 over 8 I1. It will still be correct. And 12 over 8 can be 1, it can be expressed as a decimal, 1.5 minus, the same applies with 27 divided by 8. It can also be expressed as a decimal, and it will give us 3.375 I1. Right, so we can now take it as it is to substitute now into our equation directly, and that will give us 8 I1, right, plus 30 times 1.5 minus 3.375 multiplied by I1, right, is equal to 12. Right, so simplifying further, that will give us 8 I1 plus 45, that's 30 times 1.5 minus 30 times 3.375, that's 101.25 I1 is equal to 12. Right, adding the like variables and transposing the constants to the other side, we have minus 93.25 I1 is equal to 12 minus 45. There we are. Right, so we've just added the like variables there. So we have minus 93.25 I1 is equal to minus 33, right? We therefore divide by minus 93.25, divide by negative 93.25, and that will definitely give us I1 being equal to 0.354 amperes positive, right? It means, therefore, we can go in and substitute into the I2, that the equation for I2 we had created the 1.5 minus 3.375 times 0.354. And we will definitely get 0.30 0.0306. In this regard, if we substitute correctly, we get 0.305. Is still fine. That marks our current I2 there. So the magnitudes of the two currents I1 and I2, they are therefore going to be the ones we're having now there, right? So that marks I1, that marks I2. Let's quickly go to the next question. Our next question is saying, determine, right? So I'll just clear off. The next question here is saying, calculate, okay, let's just go there. All right, it's saying there is a phasor diagram in the saying study the phasor diagram in figure 2 and determine the following. Number 1, the supply current, which means we want IT. And what do we notice here? We notice IR, we notice IL, and we notice IC. Then we have IL minus IC on our phasor diagram. Apparently, the information we have there is in tandem with tallying with the parallel RLC circuit, which means we have a parallel RLC circuit. Therefore, in order to calculate IT in such a circuit, we obviously have to use IT. The formula is equal to the square root of IR squared plus IL minus IC bracket squared, and bear in mind that this depends on which one is bigger than the other actually. So we are saying IR, our current, it's 0.5. So we are simply substituting now 0.5 squared plus, right, IL 3.5 minus IC 3.15 bracket squared under the square root sign. So that's what we have there. And that will give us 0.61 amperes. That marks our IT. Right, let's go to the next question. The next question is now saying determine the phase, right, the phase angle. Right, for the phase angle, we can calculate the phase angle as theta is equal to upturn. Remember, it's a parallel connection. How did we know? According to the information that we've been given, IL minus IC over IR, or theta is equal to up cos of IR over IT. We can do that. Or we can say again, theta is equal to arc sine of IL minus IC over IT. The supply current will still be correct. So I will use this one. So directly is arctan of 3.5 minus 3.15 over 0.5 that we have. So our phase angle is going to be 39.992 to 3 decimal places according to the instructions. Right, let's quickly go to the next question. The next is saying the value of the resistor in kilo ohms. Right, so how are we going to get the value of the resistor in our case? Right, that's the R apparently. Right, so 2.2.3. R is equal to, now in a parallel circuit, R is equal to V over IR. Right, here is how it really looks like our circuit. Our circuit looks like this. This is how the circuit is looking like. We have the capacitor, we have the inductor, right, and we have the resistor. Right, that's what we have there. Right, and the three are in parallel. Right, how did we know? Because of the currents. IL, IC, IR, and then we have a supply voltage. So of course we've been given the supply voltage, it's in AC, and also we've been given the frequency. That information is already has it been given 750 6 megahertz. Okay, so what do? We now want to calculate R. So R is equals to V over IR. So with the V that we have, that's 750 apparently, divided by IR, which is 0.5. Why? Because all these components, they share the same voltage because they are all in what? They are all in parallel. So they all have the same voltage. So we are saying for R, IR is here. We have IL is here. We have IC, it's here. Right, so that's our circuit then. So if we divide 750 divided by 0.5, right, we get 1,500. But there's an instruction there. So we are saying we are getting 1,500. There's an instruction, it's saying giving your answer in kilo ohms, right? If you press the button on your calculator, there's a button that is written ENG if you are using the Casio calculator, which we often advise that it's good to actually to use. Right. So if you press, you get your answer directly as 1.5 times 10 to the power of 3. So it's kilo already because kilo is 10 to the power of 3, 1.5 kilo ohms, right? So that's 2.3. Let's go to 2.2.4, inductive reactance. Calculate the value. So calculate the value of the inductor in a microfarad, right? That's an error which needs to be corrected. It has to be in microhenries. Why? Because we measure inductance in henries, not in farads. We measure capacitance in farads. So that was just a typing error there that was there. Right. So let's then calculate it. So first things first, we need to calculate XL, the inductive reactance. How are we going to go to calculate it? V over IL is how we are going to calculate XL. Right. So we substitute again 750 divided by IL, we already have it. That's the 3.5 that we have, right? So what do we get? We get 214.286 ohms. That marks our XL. Now, immediately after getting XL, we can then we can use it now to find L. So we are saying XL is equal to 2 pi FL, right? Making L the subject, it means we can divide by 2 pi F, we can divide by 2 pi F, right? So it means we now have L is equal to XL over 2 pi F. Right, so what is our XL? That's 214.286 divided by 2 pi. 2 pi multiplied by 6 times 10 to the power of 6y, because it's 6 megahertz. Mega is 10 to the power of 6. Right, so if we punch this on the calculator, we get 5.684 times 10 to the power of negative 6, which is the same as 5.684, right, microhenries. Micro is 10 to the power of negative 6. That marks our calculation there. Now, the next question was saying the value of the capacitor in picofarads. So the value of the capacitor in picofarads, it means first things first, we have to calculate XC again. So we are saying XC is equal to V over IC. And that's 750 divided by 3,15, right? And that is going to give us 238.095 ohms. Right, immediately after doing that, we can now relate to say, okay, how in the first place can we calculate, how in another way can we calculate XC is equal to 2 pi FC, right? Cross multiplying there, we end up having 2 pi F XC C, so that's XC there, right? Let me write it properly so it doesn't confuse. That's XC, right? C is equal to 1. So divide by 2 pi fxc, divide by 2 pi fxc. That is going to give us C is equal to 1 over 2 pi fxc. And then substituting what we already have, 2 pi multiplied by the frequency, 6 times 10 to the power of 6, multiplied by XC, we have calculated 238.095, right? And that will give us, initially we have 1.114 times 10 to the power of negative 10, right? But then we want it to the power of negative 12, both that's pico. So if we press the ENG button once, we get 111.40, that's 409 pico, that's 10 to the power of negative 11 now, picofarads. That's our capacitance. We've arrived at that. Let's quickly go to the third question. Right, question number 3 saying a semiconductor diode is under semiconductor diodes and transistors. Is saying with reference to the formula below, briefly describe how the change in length as well as the change in cross-sectional area will affect the resistance of a strain gauge transducer, right? Formula R is equals to rho L over A, right? We can simply say the longer the length of the conductor, the higher the resistance. The shorter the conductor, the lower the resistance. The larger the cross-sectional area of the conductor, the lower the resistance, and the smaller the cross-sectional area of the conductor, the higher the resistance, actually, to explain the variation between resistance and length and the resistance and area. That's basically what is happening, right? Let's quickly go on to the next question. The next question is now saying, there are few diodes that are designed to serve special purposes. With this in mind, under the following regarding the special diodes below, right? It's saying draw the IEC symbol for a photodiode. So the IEC symbol for the photodiode looks like precisely this. So there it is, right? There is our diode. There it is. Normal PN junction diode, but because it operates using the light, it means we have to indicate now the incident of light onto the panel, onto the PN junction. So these are the arrows there I am indicating, pointing towards the diode, So there we have them. Okay, that's marking the symbol for the diode. Right, draw the characteristic curve of the varictor diode. So the varictor diode is also known as the varicap of the variable capacitor. Right, so that's the variable, the varictor diode. Right, here are our characteristics, right? This is how it is. We have capacitance in picofarads here, and we have the velocity, the voltage. There we are, this side. So we have the negative because it operates actually in the reverse bias mode, right? So we have our -2, 1, 2. Okay, this is what we're having there. Okay, so this is -2, -4, -6, -8, -10, -12, and -14, right? And then here we have that's 20, that's 40, that's 60. It's indicating the capacitance, right? And that's 80 there, right? And then we show the inverse proportionality that tends to take place, right? So that's how it's gonna be. Okay, there we go. It's marking the characteristics of the varictor diode. That's how it is. Right. So let's now quickly refer to the next question. Name 3 points to be considered when a transducer is selected for a particular application. Right. What are to consider? Number one, consider the physical quantity to be measured, the accuracy required. Secondly, thirdly, we can convert in principle which is most suitable, and also operating range, also sensitivity, also stability and reliability. That's 3.3. Those are the points to be considered when a transducer is selected for a particular application, right? 3.4, a voltage multiplier is a special type of diode rectifier circuit that can potentially produce an output voltage many times greater than that of the applied input voltage. Draw a neat labeled half-wave voltage doubler, right? So that's how it looks like. So I'm gonna draw it here. I'll just quickly erase my board. I saw 3.4.1. Number one, we start here with a transformer. So we have the transformer here. Okay, there we go. Then, of course, there's the circuit symbol for the transformer. Okay, let me just draw it a little bit accurate here. Right, there we are. I'm going to indicate there's a point here that I'm going to indicate as A. There is another one again that I'm going to indicate as B. Okay, that's B there. Right, then I have, after that, there is a capacitor here with the positive and the negative, right? And then we have a diode that is connected in parallel. There is the diode here. Okay, right. There is the diode. And then we have another diode again here at this point. So we shall label this one T2, right? And there is our capacitor. Okay, here. So we call it. Of course, we have our 2 VM this point. That's positive, that's negative there. Right. So again, we are indicating this as positive, we are indicating this as negative, and we are calling this VM here. Remember, it has to be labeled our half-wave voltage doubler. Right. That's our circuit there. The next question is saying, give a short explanation of the working of the half-wave voltage doubler. Right, so let's just quickly explain. I'm just going to quickly explain. Right, so during the positive half cycle, when A is positive with respect to B, right, diode D1 is forward biased, and diode D2 is reverse biased. So we see them, they have been labeled there. Therefore, it conducts diode D1, charging capacitor C1 to peak voltage Vm. That's the first point. Right. Secondly, during the negative half cycle, D2 is forward biased and D1 is reverse biased, charging capacitor C2 to the peak voltage 2 Vm. That's the explanation that is expected, or that was expected of us. Right, so I will go to question number 3.5. Describe the process of acceptor doping as applied in the atomic theory. Right, that's 3.5. Right, in simpler explanation, we can say if a trivalent atoms, or if trivalent atoms such as indium, gallium, or aluminium are added to pure silicon or germanium, they form covalent bond with one another. right? One of the silicon germanium atoms are left without a covalent bond and create an absence of an electron, a hole. And these holes tend to attract electrons. These trivalent atoms are also known as acceptor atoms. That's the explanation we were to give there in points. Right. State the operating principle that the photosensitive transducer uses. Right. The voltage is generated as soon as an incident light falls on the PN junction. So the photosensitive transducer, it is light dependent. So voltage will be generated as soon as incident light falls on the PN junction. That's 3.6. So I'll go to 4.1. Question number 4, semiconductor transistor and operational amplifiers. Draw a neat labeled characteristic curve of an N-channel JFET, right? So we want the characteristics of that. So I will erase this. That marks 4.1, right? So here are the characteristics of the JFET. So I'm going to indicate them as this, right? Here we are. That marks our VDS. And that marks in milliamperes. Right. So we're going to indicate them. Okay, there we are. Okay, there we are. Okay, and there we are. And lastly, there we are. Right. So we have a negative. So that's the VGS, negative 2 volts. VGS, negative 1.5 volts. VGS, negative 1 volts. VGS, negative 0.5 volts, and VGS, 0 volts. Okay, that's our diagram there, right? That's our diagram. Right, that's our characteristics, right? Then here we now indicate, right? That's 2, 4, 6, and of course 8 there. I'll try to space them a little. Okay, there we are. So we have 2 here, and we have 4 here at this point. We have 6 there, we have 8 there. So there they are, 2, 4, 6, and 8. And then, of course, here, I'm going to indicate right at this point. That's max VP there. But then we have 5. We have together with there's 10 there, and also there's 15 here. Right, this marks our characteristics. Right, let's quickly go to the next question. The next question is saying, draw a neat labeled, okay, current regulators are used for keeping the supplied current constant irrespective of the variations in load resistance or input voltage. Truly. Now draw a neat labeled circuit diagram of a constant current regulator. Right, so we'll just have to draw it clearly there. Right. Right, so here I will indicate my RE. Then I have, that's my, okay, I'll try to make it a little bit, okay. Okay, there is my transistor there. right? Okay, so that's my PNP transistor. I have the resistor, another resistor again here. That's my RB, right? And then okay, that marks the load resistance there. So label this RL, and apparently this is the V out regulated, and then this is marking, right? I see, I have, okay, there is at this point we have we're going to indicate right in between here we have VL, and then we have IC being equal to IL, apparently resistance, and of course we have the current, right, we have another connection right at this point of a Zener diode right there. We have the Zener diode at this point here, right? Right, and then we have VBE in between. That marks RE here at this point, and this is now VRE right across. We're marking VRE, right, and then right across here we have V in unregulated. So we have to indicate it as well, unregulated. There it is. And then positive, of course, here, and negative at this point. Again, positive, and then negative. Again, positive, and then negative. Of course, positive again at this point, and negative at this point. This is now marking our constant current regulator, right? Our constant current regulator is per instruction, right? This is our circuit diagram, right? Let's quickly go to the next question, right? Our next question is saying, draw a neat labeled circuit diagram of number one, the integrator op amp. So let's start with the integrator op amp. That's 4.3.1. So I'll label it 4.3.1, right? This is what we have. Number one, I'll indicate R1 here. Then we go, that marks, okay, there it is, with positive here, negative, and I have the feedback with the capacitor in between, and then I have the output, right, and then interconnect with the output, right, and then we have the negative terminal grounded, so it is grounded indeed, there it is, and then at the far end we have there we are. So this is marking V1, that's R1 there, and that's C1 there, and that's V out. So it's clearly labeled. That's 4.3.1. Let's go to 4.3.2. Right, for 4.3.2, I think the summing op amp. So we want the summing op amp. So with the summing, there it is, right? We have to indicate the resistances or the resistance that it's having. So I just indicate from here. right? So there we are. Okay, resistance, right? And then the other one again. That's making our other resistor. Okay, there is marking resistor R3. Okay, that's marks resistor R3 there. Right, there we go, there we go. Right, R1, R2, and R3. Right, they are all interconnected. There is the interconnection directly to them. Right, F, the feedback resistor. So we have, and there we go. That's okay, there we are. And then we have the positive. Right. Let's try to make it a little bit neat. Right, there we go. And then we have RF at this point. That marks our feedback resistor there. Right, then they are interconnected. That's the feedback. That's the feedback, and apparently it's a negative feedback. And then we have V out, and then of course it's grounded. So we ground it. Right, we have the earth, the virtual earth. That's our virtual earth there. And then we have, of course, the connection from this point. So there we are. There we are. That marks our summing op-amp. This is our summing op-amp, right? This is V1, by the way, and this is V2, and this is V3, right? That's how our circuit looks like. Right, let's quickly go to the next question. The next question was saying, right, question number 5. No, 4.4 actually. Right, 4.4 is saying the characteristics curve of a common emitter amplifier is given in Fig 3. From the information given, calculate the values of the following. Number 1, VCC. And apparently, a VCC, it is just an interpretation of the characteristic curve, is equal to VCE, by the way, and is equal to 20 volts. That's VCC there. Then RC at the operating point, the quiescent point or the operating point, right? So we want RC there. So RC is going to be equal to VCC, which we said is equal to VCE, over IC. So it's going to be the VCC at the quiescent point is actually 12. We see it there, right? This one, right? So we are saying 12 divided by, so we are taking right at this point here, that's our operating point, divided by what is the current that is corresponding with that point in this. That's divided by 6.5 actually, that's 6.5, right? But it's in milliamperes, so we mustn't forget it's in milliamperes. So it's 6.5 times 10 to the power of -3, and that will give us 1,846.1538, which is apparently 1,846 kilo ohms. That's our RC. Right, let's go to the next question. It's saying calculate RB at the operating point if VBE is equal to 0.7. So at the operating point again, RB is equal to VBE that we've been given divided by IB at the operating point. And IB at the operating point is this one now that we are taking. So it's going to be 0.7 that we've been given divided by 40 times 10 to the power of -6y, because it's microamperes. So 0.7 divided by 40 times 10 to the power of -6, that's giving us 17,500, which is apparently 17.5 kilo ohms. So we've calculated that. And let's quickly go to the next question. The next question is saying it's on measuring instruments. So it's saying draw a neat labeled block diagram of a continuous balance digital voltmeter. So I will quickly draw it here. Right. Number one, we have right. So I'll start with the comparator right at this point. Right. So I'll indicate it here. Right, apparently, that's our comparator there. So we'll label it comparator. Right. Comparator. Right, and then they're connected. I'll indicate. There we are. Right. Okay, and then we go to the counter. Marks our counter there. Right, and then, of course, to the reset. Okay, there it is. And from there, we now go to the display, the LCD display. So that's right. That's the one we have here with the digits, of course. Here we are. Right, there we are. Right. Okay. There it goes. So the display there, and then we have the digital to analog converter, and then of course with feeding back to the comparator and with an analog and non-voltage that marks our diagram there, our block diagram. Right, let's quickly go to the next question. So the next question was saying, describe the following terminology by referring to the silicon controlled rectifiers. The holding current. So holding current is simply the minimum current needed to hold the SCR in its conducting state. So if it goes below the holding current, it switches off. So it's very important that it always remains above the holding current if it is in on state. Then the delay angle, it is the time the SCR is off or delayed before it starts to conduct. That's the delay angle. Right. Then the next question was saying, draw a labeled IEC symbol for the silicon controlled rectifier. So the symbol for the silicon controlled rectifier is this one. Actually, it is like this. There it is. Right. It has the anode. It has the cathode. Right. There is the anode here. And then there is the cathode. Right, there is the cathode here. Right, and then, so I will try to just make this a little bit straight, right? So we have this, and then there is the gate. So it's almost like a diode, like there we are. But then there is a gate here. Right, there's the gate pulse. There's the gate. There is the gate where the gate pulse is. Right, fired from. Right, there we are with its three terminals. Right, so that's this IEC symbol for the SCR. Let's quickly go to the next question. So our next question is saying, a sine wave is displayed on the screen of an oscilloscope shown in figure 4. The horizontal and vertical settings are as follows. Right, volts, div 50 millivolts, time division again 20 milliseconds. Calculate the following. 5.1, the RMS value of the waveform. Right. So number one, VRMS is equal to V peak to peak over 2. So we first need the peak to peak voltage. So in order to calculate the peak to peak voltage, V peak to peak is equal to V peak to peak is equal to, right, from the negative, like we are taking that on our diagram. What we do is we count the number of blocks from the negative peak to the positive peak right here on top. So if we count, we have 1, 2, 3, 4 blocks. So we say for the number of blocks, multiply by the voltage we have been given here, which is 50 millivolts. So we say 4 multiplied by 50, and that will give us 200 millivolts. That's our V peak to peak, right? So when we are now calculating VRMS, we simply say V peak to RMS, right? So divided by 2, right, comma, and that gives us 70. That's our VRMS. Let's go to the next. Is average volume, average value of the waveform. So for the average value of the waveform, right, again, we are saying V average is equal to V peak to peak, the peak to peak voltage over 2, multiply it by 0.637. So 0.637. So we have already calculated V peak to peak, 0.637. So we simply come and say 200 times 10 to the power of negative 3 divided by 2 multiplied by 0.637. So we get 63.7 millivolts. Right, that's the average value of the waveform. Then the frequency of the waveform. So for the frequency now, we are to first calculate the number of blocks in the full cycle, right? That's how we take measurements on the oscilloscope. So the full cycle, just any full cycle starts from here, right up to this point. That's a full cycle. So how many blocks are there? We have 1, 2, 3, 4, and 5. So those are full blocks. So F is equals to 1 over T. Indeed, I'm doing 5.4.3. Right, so it's equal to 1 over, right, our time, the time taken to complete a full cycle is going to be the number of blocks we have. In this case, we have 5. Multiply by the time we have been given, the time then is 20. So we say 20 times 10 to the power of negative 3, right? So that is going to give us 10 hertz if we calculate that. So that marks the end of our revision, just like that, okay?